focal length of a concave mirror and focal length of a convex lens. What are the important points to be remembered in this experiment? Now, if you take a concave mirror, it's a very easy experiment. You will keep an object in front of the concave mirror and find out the image and adjust it for parallax error. Then measure the object distance and image distance. While measuring object distance and image distance from a concave mirror, remember, both are measured from the mirror itself. So you can take the direct reading in the scale. So no problem. So mirror is here. This is a mirror. I'll change this color. Yeah. So this is the mirror. And you measure the object distance from the mirror. Here is a notch up to this object. So this is the object distance. And again, from the mirror, that is from here to the image pin. That is image distance, which is given here. So all the distances are measured from the mirror. So whatever reading is written here, that becomes object distance. And whatever reading written here becomes the image distance. So object distance and image distance are the same readings that you count here. Whereas in lens, distances are measured from the lens and the object and the image come on either side of the lens because it is refraction which is happening. So in the case of a lens here, you see that I will discuss both simultaneously. Last time the mirror was here, but now the lens is here. So refraction is taking place. Light is passing through the lens. So now the object distance is this one from the object to the lens, and from image lens to the image pin, it is the image distance. So if you record this value, then it becomes object distance. If you record this value, it will not be image distance. Because it will start from 0 here. Suppose this is 0, this is 10, this is 20, and if this is 30, if this is 40, and if this is 50, of course, you have to take even point values also. It will be an ordinary scale. You will have 50.1, 51.2, something like that. This is 60, 70, 80, 90, 100, 110, 120, 130, say. Then 130 is not the image distance. Object distance 50 is correct. What is image distance? Image distance is 130 minus this 50. 130 minus 50, that will be 80 centimeters. That means from here to here, you have to calculate this distance. So 80 centimeters. That's the main important thing. Whereas in a mirror, the reading itself is the distance, distance to be measured because mirror is in the 0th position here. So this reading itself is object distance. This is image distance. Okay, so you measure them in a concave mirror experiment. You measure for different object distances. You measure the image distances. Then just use the formula F equal to UV by U plus V. And this is a ready-made formula with all sign conventions put. So measure this. This should be consistent, that's all. It should be around 20. And if the focal length of the mirror is 15 centimeter, it should be around 15. So whatever the value you get here, it should be very close to other values also. Then average value, that is the concave mirror experiment. Very simple. And if you want to know what is the parallax, it should be like this. If it is a parallax, and while setting for parallax, you have to see that, yeah, this is the mirror. Of course, this is not made to stand on a optic bench, but you can see how to set it for parallax error. Now, if you see the image pin, now red pin is object pin and blue pin is image pin. The tip of the image pin should be coinciding with the object pin and they should move together equally. So as you move your head, object and image pin should move together. Then it is set for measuring distance. Now there is no parallax error. So suppose you change the position of the image, then they don't move together. Now they move together. So they should move together throughout. The tips not only coinciding with each other, they should move together. So object and image should move. Now image pin is blue. Object image is the inverted image of the red. So they are moving together. Yeah. Yes. Yes. They are moving together. And if you change the position, they won't be moving together. They will be separating. Okay. So that's how it is set. Okay. Then, so that is how it is done in concave mirror. Now, in convex lens, here we draw the graph. The experiment is done like this. It is set for, again, parallax. If you want to see how it is done, yes, you see. Through the lens, there is a red object or a purple color object on the other side. Its image is seen inverted here. You can see the image inverted. This is the image pin which is used to locate the image. So if you see that the tips are moving together, tips of the two pins are moving together. So now it is set. You can measure the object distance and image distance. Whereas if it is not set properly, then it will be like this. Now it is not set properly. The object and the image pins, they are not moving together. So this is the wrong setting. Okay, you know this, you have already done experiments and you know this. That's how it is set and the readings are taken. And once the reading is taken, while in drawing the graph for convex lens, you should be extremely careful. See, you get object distance and image distances. Some people worry whether when you increase the object distance, what should happen to the image distance. Distance should go on decreasing because image must come closer and closer as you move the object away and away in convex lens. So as the object distance increases, image distance from 42, it is decreasing. Okay, now you know that for a convex lens, object distance and image distances will be equal when the object is at 2f. So if the focal length is f, and say this is 10 centimeters focal length, and if this is 20, when the object is kept at 20, that means 2f, a same sized image is formed at 2f. So like this. So that principle is taken here in the graph. So in the graph, so very, very careful. You should be very, very careful while drawing the graph. Main important thing. You may start from 18 centimeters or 20 centimeters because you know that up to 18, 20 centimeter, there are no values below that 20 or 25 here. So the minimum value itself is 26 here and 26.6 here. You may start it from 20. But what the scale you choose here, 18 to 20 centimeter, this is 20. So 2 centimeters for one division. Same scale has to be taken here also, 2 centimeters for one division. Then 22, you can see that. Then 24, similarly here, 20, 22, 24. So the values, the scale that you choose in both the x and y axis should be same. And they should be starting with the same value. So this is 18 for x-axis, 18 for y-axis. Of course, we have squeezed the graph. Okay. So once you take such a similar scale, you mark the points. Points will be somewhat, they will be having a, when they are joined, they will form a curve like this. You see here, the points are here. Some of the points may not lie in the scale. Okay, no problem. But let they be in a smaller number. Most of the points come under the scale, this curve. So once you join the curve like this, you have to draw a 45-degree line. What is 45-degree line? Don't join these things like this. Some people join it like this to the center. They select randomly some points and join it to the center. No, it's completely wrong. You will lose all the marks for the practicals. So you should draw a 45-degree line. Well, what is 45-degree line? 45-degree line is a line which gives object and image distances same. So you know that, and one more thing that is to be taken care of is the whole graph doesn't come in the first quadrant. It comes in the second quadrant. So this is first quadrant. If you take object distance along plus x-axis, image distance along plus y-axis, then it is first quadrant. But here is object distance negative, minus x-axis, image distance positive, plus y-axis. Then you are choosing this quadrant, and that is this whole graph. You can see the whole graph in the second quadrant starting from 0 here. So that is very important. Don't draw it in the first quadrant or some other quadrants. So once you select the second quadrant, now where is u and v same? You know that object distance is equal to image distance when Object distance and image distances are same for a convex lens. When the object is at 2f, you have to search that point in your curve. You have drawn curve for different u and different v. Among them, when u and v are same, that's what you have to search. Why this 45-degree line gives u and v same? For example, when you see the 45-degree line, if you, for this point, for example, if you observe this, then this is 22. This is also 22. You take another line, if you draw a 45-degree line, then you will find that if this is 26, this is also 26. But whether these values are the focal lengths of the lens? No. That line which gives u is equal to v in all its positions, that 45-degree line cuts our graph somewhere here. So it is cutting our graph here. From there, you have to find out note down the values. So first of all, draw the graph, join the points, draw a 45-degree line. Before that, your scale should be very proper, because whatever the scale you have chosen in the y-axis, same scale should be chosen in the x-axis also. The value should be identical. Now, wherever this 45-degree line cuts your graph, you drop the lines like this. Find out these values. Whatever the value you get here, the same value must be found here also. This is the place where our graph shows u is equal to u is equal to v. Object distance equal to image distance. What is that? Object distance is equal to image distance. This is u equal to v, u equal to v. That is 31, I think, 31 centimeters. Because this is 30, this is 32. Middle one is 31. This is 31 centimeters. This is also 31 centimeters. 30, 32. Middle one is 31. That means this is the 2f position. 2f is 31. But what we do here is we add this 2f. This is also 2f, because you know that object and images will coincide, or sorry, not coinciding. They will be at the same distances. When the object position is 2f, image position is also 2f. So if this is 2f and if this is 2f, add them, then it becomes 4f. So how to find out f? 4f divided by 4. Then it becomes f. So that means this 31 plus this 31 divided by 4. That gives 62 by 4. That gives 15.5 centimeters. That's how we find it out. So remember the important points. The two scales must be identical. They should start from the same value and they should continue. Either you can start from 0, but here starting from 0 is not needed, because you don't have many values between 0 and 20 centimeters. So you can start from 20 or 18. Let the scale be same in both the axes. Mark the points, draw the line, draw the curve, and then draw a 45-degree line by joining these corners where you have u equal to v. Then connect it to the graph. Where does it cut the graph? Find out this value, add them, divided by 4. You will get focal length. That's what is done here. 31 centimeter divided by 4, that is 15.5 centimeter. That's how it is done. Okay. Thank you.